So let's take a look at the applications for linear equations. And because you guys are largely all in veterinary stuff, we're going to focus mostly on some applications that come from veterinary sciences or problems involving animals at the very least. But I do want to emphasize, obviously, there are applications outside of this. I just figured I would go with the kind of stuff that you guys might be most interested in. So one type of problem that we might want to work out here is, let's suppose that we have an animal that needs to lose weight or maybe needs to gain weight. We can do similar kinds of problems both ways. And we want to come up with a model for how much that animal is going to weigh over time. So let's say that a dog weighs 20 pounds and gains 2 pounds per week. And we want to write an equation for the weight in pounds versus the time in weeks. Well, the way that I'm going to do this is I'm going to start off by coming up with some variables. Now, that might seem like, well, obviously you need some variables, but it's a good idea to be careful, make sure that we've really got everything done correctly. So even though it seems maybe a little bit simple, let's start off by saying, let W be the weight, which I can't spell apparently. That is supposed to say weight. It says, I don't even know what at this point. There we go. That looks a little more like the word weight. And T, the time. Now, of course, W is going to be the weight in pounds, and the time is going to be in weeks. That's given to us in the problem. Now, what we know about this is that this dog gains 2 pounds per week. So that means that the slope will be 2. It's going to be 2 pounds per week in particular. Now, this is another place where dimensional analysis can help you out a little bit. Which, remember, dimensional analysis is just a fancy word for saying we're keeping track of the units and making sure that the units work out. It's really all you're doing. The point is that changes in weight need to be in pounds per week. So the reason that this matters is because you want to be careful. Like, maybe I don't tell you do the time in weeks. Maybe I don't tell you do the weight in pounds. Well, if this is given in pounds per week, then you had better measure your time in weeks, and you had better measure your weight in pounds, or else you're going to have to convert this rate of weight gain into whatever units you do want to use first. In this case, we're just going to measure weight in pounds and time in weeks. So then what we know is that the weight is going to be equal to 2 times the number of weeks, because it increases by 2 per week. But then we have to add on the original weight. And the original weight is going to be 20. So this is the rate of weight gain. I don't have room to write rate of weight gain, so I'm just going to say that out loud. And then this is going to be the initial weight of the dog. So this is one thing that you can do with these kinds of equations. You can kind of describe how much is the dog going to weigh over time. Now, why is this important? Well, there are various reasons why you might want to do this. So I'm going to leave what we have down here, and I'm going to give like a part 2 to this question, because maybe this is what we're really interested in. So let's ask ourselves, when will the dog weigh 25 pounds? And I'm afraid that I sort of ran out of room over there, but that's supposed to be a question mark. So in practice, this is probably a dog that's underweight, but it's probably not necessarily that much underweight. We really want the dog to weigh 25 pounds. It only weighs 20 pounds, but we don't want to like leave the dog on this high calorie diet forever and end up with this obese dog. So we want to predict how long are we going to have to keep the dog on this diet so that we know like how much food do we want to get hold of and things like that. When should we expect to recheck the dog to see if it's gotten up to that weight? Well, the answer is that this amounts to solve when the weight is equal to 25. So in other words, I take this equation and I plug in 25 for W. That should be equal to 2t plus 20. And I solve this for T. That's the number of weeks that I'm going to have to wait before the dog weighs 25 pounds. So if I subtract 20 from both sides, I get 5 equals 2t. That gives me 5 halves equals t, or t equals 2.5. And of course, that is in weeks. So the answer is it's going to take 2.5 weeks for the dog to go up to 25 pounds. We're making this poor dog gain weight really fast in this example, I just realized. But fortunately, it is a fictional example, so hopefully that is not a big deal. So that is one application. Now let's take a look at another kind of application that you can do with these linear equations. So let me suppose that I give you the following problem. Let's say that a rabbit got sick, and 5 days after becoming sick, he weighed, man, I have trouble writing the word weighed or weight or anything like that. Let's say 1,800 grams. And 12 days after he weighed, let's say, 1,710 grams. And we want to find an equation for his weight and estimate how much he weighed when he got sick. Okay, wow, that was a lot of writing for this problem, and we barely have any room to work this thing out. So I'm probably going to depend upon you guys to write this down, and eventually I'm going to erase part of this so that we can actually have some space to work this out. Anyway, so first of all, we got to come up with variables, and I didn't give you units this time, but the units that were given are grams for the weight and days for the time. So I'm going to say let's let W be the weight in grams and T be the time in days. And we will consider 0 days is when he gets sick. Okay, so T measures the number of days that it has been since he has gotten sick. Now, this is a little bit weird because it means that day 0 is literally the first day that he came down with the sickness. That's not day 1. You might think, oh, that's day 1 of his sickness. Yeah, it's the first day of his sickness, but it's really T equals 0 in this variable. So if he got sick on a Monday, that Monday is considered day 0. This is a little bit like the problem, if you've ever noticed it, with the way that our method for measuring years is, or centuries, I should say, measuring centuries in our Western calendar system that is commonly used in America and also Europe and, like, I don't know, Australia, probably, and who knows. Other places, some of them use it too because it's used a lot in international business. Point is, right, we have like the 1st century of the Common Era. Well, the problem is that 1st century Common Era is actually the years like 1 through 100. But you would think, oh, 1st century, that should be like the 100 years, like 100, 100, and, it should be like 150. That should be first. Well, no, that's actually 2nd century. So the 2nd century is the stuff that begins with a 1, not with a 2. It's confusing. So it's because people don't want to talk about century 0 being the years from 0 to 99. And this throws everything off. Had this calendar system been invented by mathematicians, it would make so much more sense. So much more sense. Anyway, moving back to the problem at hand, hopefully the little calendar diversion here didn't throw anybody off too much. The point is that t equals 0 is when he got sick. So presumably, this is the kind of situation that could really happen in some cases, okay? So maybe an owner notices that their rabbit got sick, but maybe they didn't call that day and bring him to the vet. Maybe they waited a day or two, and then they said, well, it doesn't look that severe. We'll just take an appointment in a couple days whenever you can fit us in. It's not an emergency. So you may not actually see the rabbit until 5 days after he gets sick. And then maybe the vet says, well, look, bring him back in a week. So that's 12 days after he gets sick. And we'll weigh him again. And then you notice, oh, hey, he's losing weight here. So let's see, we want to know not just how much did he lose over that week, but what do we think he probably weighed back before he started getting sick? When he got sick, what was his original weight? So that we can know how much did he actually lose. Assuming here, of course, that he's losing weight in a linear fashion. That may not be a great estimate in the long term, but maybe it works okay in the short term in this problem. Okay, so moving back to the issue at hand here, what we have here is 2 points. The points that we have are that at 5 days, he weighs 1,800 grams, and at 12 days, he weighs 1,710 grams, or 1,710 grams. So this means that the slope is going to be 1,800, or I'm sorry, not 1,800. Let's take, this is our second point, this is our first point. This would be 1,710 minus 1,800 divided by 12 minus 5. This is going to be negative 90 over 7. And by the way, this would be in grams per day. So his weight changes by negative 90 over 7 grams per day. If you wanted to work out how many grams per day that actually is, that would be, let's see, 10, and then another. It's almost 13 grams a day that he's losing. If you wanted to convert this into decimal, it would come out to be like 12.8 something grams that he's losing. The negative indicates that he is losing weight. So if we were simply asked, how fast is he losing weight, this would be our answer. But that wasn't our question. Our question in this case was to find an equation. Now, I'm going to erase the actual question here because I have no space to write. So now what I can do is I can find an equation by just using point-slope form. And I'm just going to take this, excuse me, I bit my tongue somehow while I'm talking. I'm just going to take this point as my point for the point-slope form. So I'm going to say that W minus 1,800 is going to equal negative 90 over 7 times t minus 5. And this is an equation for his weight. But really, we probably don't want it in point-slope form. We probably want an equation that gives us the weight in an obvious way based upon the time. So let's solve for W. That would give me W equals negative 90 over 7t. And then we're going to have plus, let's see, 5 times 90 is going to be, well, 5 times 9 would be 45, so 5 times 90 would be 450 over 7. And then we have plus 1800. So to get a common denominator here, I could multiply by 7 over 7. So this is going to be negative 90 over 7t, plus then we're going to have 450 over 7 plus, let's see, 1800 times 7. So 1000 times 7 would be 7,000. And then 7 times 8 is 56. So 7,000 plus 5,600 is 12,600. Let's just make sure we did that correctly. 5,600, and then another 7,000 would be, 12,600. Add another 450 to that, and we are going to get that W equals negative 90 over 7t plus, and then we're going to have 13,050 divided by 7. And now, if we want to know what was the original weight, what was his weight when t equals 0, well, that's just going to be the W-intercept. In other words, what we get when we plug in t equals 0. So the initial weight here is going to be this 13,050 divided by 7 in grams. Now, I don't know what that comes out to be off the top of my head. You probably want to get some kind of an estimate for this. So I would say, these are the kinds of problems when you have an applied problem like this, where you do probably in the end want to come up with some kind of a decimal answer. You don't necessarily want to leave this thing just as a fraction like this. But I will leave it to you guys to plug that in. Now, I can see this is going to be, let's see, if it were 14,000, then this would come out to be 2,000 grams. So 1,000 less than this, it's going to be like 130 less. So he probably comes out to be like 1,870 grams back at the beginning. But like I said, I don't know. I'll leave it to you guys to come up with the exact number since I don't have a calculator on hand and I don't feel like bringing one up and taking time to bring that up on my computer or anything. So plug this into a calculator. I trust that all of you guys know how to do that, and then that will give you the estimate for the initial weight. So as you can see, there are various types of problems that can be modeled using these linear equations. Now, I do want to mention a few things about the limitations of linear modeling like this, okay? The problem is really that a lot of things in the real world, they don't change at a constant rate. So in order to be modeled by a linear equation, the relationship between two variables, it has to change at a constant rate. Sort of the defining feature of linear relationships is that the rate of change between the two variables is constant. So what does this mean? Well, what it means is because it's usually not constant in the real world, you often can't use linear equations to model things, at least in the long term. But sometimes, even if you can't do it long term, you can still do it short term. You can still say, well, over a long period of time, the rate changes quite a bit. But over the short period that we are interested in, the rate of change is pretty close to being constant. So we can at least estimate what we're going to get by using a linear model like this. All right, so hopefully these examples of building linear models and asking questions about them and answering questions with them was helpful to you guys. This kind of concludes a lot of what we're going to be covering in this. So what I would like you guys to do after this week is up is to spend the rest of your time kind of reviewing for the final exam. I'll be posting more materials for that, and I'll be available in my office hours and things to help you guys to study and review and everything. And of course, you guys are always free to contact me and ask if we can get together on Blackboard Collaborate, outside of office hours, if for some reason the office hours aren't a good time for you, or you feel like you need some extra help studying and things. So anyway, I hope that this class has been at least somewhat enjoyable. I know mathematics is not necessarily everybody's favorite topic to do, but hopefully you have found this one to be not too painful at the very least. And otherwise, good luck on your upcoming work, and hopefully I wish you guys all of the success in your careers and everything.